Niels Bohr saved the Rutherford atom from collapse by imposing a strict rule. He proposed an electron could only exist in specific, allowed orbits. As long as it stayed in these fixed tracks, it did not radiate energy. We have to be careful with the word discrete here. In physics, discreteness often means counting individual objects, one electron, two photons. But hydrogen only has one electron. The mystery was that this single electron could not possess every possible energy. The discreteness Bohr found was a restriction on allowed states. This animation of a classical planetary orbit shows why Bohr's restriction was so strange. Under classical physics, a bound object has continuous possibilities. Depending on its energy, a planet can drift smoothly closer to its star or further away. Classical mechanics does not normally dictate that one orbit exists, while the space directly next to it is strictly forbidden. Simply binding a particle to a center does not automatically quantize its motion. A trapped particle usually has an infinite number of paths available to it. Bohr's discrete orbits worked perfectly to predict the hydrogen spectrum, but because classical physics offered a continuous range of options, those fixed orbits lacked an underlying physical explanation. To find that mechanism, we have to look at a different kind of system, one that is perfectly continuous but naturally produces restricted, discrete states. Think of a musical string fixed at both ends. This diagram shows interference. A plucked string's traveling waves reflect and overlap. Crest meets trough. Most patterns destructively cancel and die away. But specific patterns fit perfectly, reinforcing into standing waves with fixed nodes. They survive in whole number increments, 1, 2, or 3 humps. The string is continuous, but its stable modes are discrete. This reveals the logic behind Bohr's orbits. Wave-like behavior, when placed under a physical constraint, naturally generates a discrete set of allowed states. The physicist Louis de Broglie brought this exact intuition to the atom. If Bohr's model demanded discrete states, and constrained waves produce discrete states, then the electron itself must possess wave-like behavior. This was a logical inversion of what had come just before. Albert Einstein had already shown that light, long understood to be a classical wave, behaved like a discrete particle. De Broglie asked the reverse. If a wave can act like a particle, perhaps a classical particle can act like a wave. In 1924, de Broglie approached this problem by returning to the earliest relationship in quantum mechanics. Energy equals Planck's constant times frequency. Frequency measures a repeating cycle. Applied to isolated energy, it must carry an internal periodic phenomenon. We visualize this as a simple oscillator, bouncing steadily. There is no propagation yet, only a rhythm at a single point. The nature of the ticking remains unknown, but the energy-frequency relation gives us a specific cycle we can now follow. Einstein's physics tells us that objects with mass contain energy even when they are stationary. Merging that with the quantum equation gives us a baseline internal rhythm for an object at rest. We will label this stationary ticking rate nu-0. Even at rest, the energy possesses this inherent cycle. Now we take this isolated piece of energy and put it into motion relative to our laboratory. The moment the object moves, the laws of relativity and quantum mechanics begin to pull the internal rhythm in 2 different directions. Watch the moving oscillator. From our perspective in the laboratory, relativity dictates that the internal clock of a moving object must run slower. This is standard time dilation. But motion also increases the object's total relativistic energy. Our quantum equation demands that a higher total energy must correspond to a faster frequency. Look at these 2 results side by side. Following the internal clock yields a sluggish rhythm, but calculating the total moving energy demands a rapid one. These values move in opposite directions as speed increases, yet both derive from valid physics describing the exact same object. De Broglie realized that frequency alone was insufficient to describe this system. He had to look for a deeper property within the cycle that could remain consistent. This diagram introduces something more basic: phase. Frequency is how quickly a cycle repeats. Phase maps exactly where we are inside that cycle. We write the equation like this. It's a way of keeping track of a periodic rhythm at any given time. Let's return to the corpuscle at rest. Its phase expression contains the rest frequency and time. But look carefully. There is no spatial variable here. Nothing says phase changes from place to place. At rest, this is simply a rhythm in time. There is no wave. But moving into the laboratory frame changes the rules. Relativity does not merely slow down clocks, it mixes space and time coordinates. By relating the rest frame time to our laboratory, we can substitute the Lorentz transformation directly into the time variable of our phase equation. The laboratory description now requires both a clock and a position. This map shows what x means. If we freeze time, different positions are at different places in their cycle. Viewed together, a familiar shape appears. This isn't matter bending up and down. It's a map of phase across space, the phase wave. What began as a rhythm strictly localized in time has been forced by relativity to become a structure extended across space and time. We now have two things in the story, a localized corpuscle and an extended phase wave. They are not the same object, and their velocities are entirely different. So why should this wave have anything to do with that corpuscle? Let's bring the corpuscle back into the laboratory, moving at velocity v and carrying its slow internal oscillator. We can evaluate the extended wave's phase strictly along the physical trajectory, where the corpuscle actually travels. When the corpuscle's internal oscillator is at the top, the local wave phase is at a crest. Halfway down, the wave is halfway down. At the bottom, the wave is at the bottom. Notice that the wave itself is not traveling with the corpuscle. Its phase crests are sweeping past it, traveling faster than the speed of light. Because these crests exceed light speed, they cannot transport energy or represent a physical substance moving through space. They are solely a distribution of phase. And yet, wherever the corpuscle actually is, the phase of the extended wave perfectly agrees with the phase of the local internal rhythm. De Broglie called this the harmony of phases. These two diverging frequencies from our initial observation represent different ways of sampling this single phase structure. This visualization shows the fast frequency. It is simply what a fixed coordinate in the laboratory sees as the rapid phase wave washes over it. The slow frequency is what you experience if you track along the specific trajectory of the moving corpuscle itself. One phase structure, two different ways of sampling it. Different observers will divide the same phenomenon into different frequencies and wavelengths, but the phase assigned to a specific space-time event remains invariant. Looking at the full phase equation on screen, we can now see where momentum enters the picture. Let's algebraically expand it. The phase has split into two pieces. One part multiplies time, and one part multiplies space. If we look at the time coefficient and substitute our original quantum energy relation, we find that the time component is governed entirely by total energy. Energy strictly dictates how rapidly a particle's phase advances through time. Now look at the spatial coefficient. Applying those same relations leaves us with a specific set of variables, gamma, m0, and v. That combination is standard relativistic momentum. This allows us to collapse the entire equation into a tight, compact form. Momentum sits exactly beside space. A particle's momentum strictly dictates how rapidly its phase advances through space. This isolated spatial sine wave directly gives us our wavelength. If we freeze time, we can bracket the distance between two adjacent crests. Wavelength is the physical distance required for the spatial phase to complete one full cycle. By setting that phase change to a full 2 pi and equating it to the spatial term, the variables isolate perfectly. We get lambda equals h over p. Watch what this means physically. As a particle's momentum increases, its spatial phase must advance more rapidly, compressing the pattern into a shorter wavelength. And as momentum drops, the spatial repetition length stretches back out. Energy set the rhythm in time. Motion spread that rhythm through space. Momentum fixed the spacing. And the spacing was h over p. This newly discovered wavelength provided an answer to the mystery of Niels Bohr's atomic orbits. Bohr had established a mathematical rule that predicted these orbits perfectly, but the reason for that rule remained a secret. De Broglie applied his phase wave to the atom. He asked what happens when the wave is no longer moving in a straight line, but is wrapped into a closed circular path around a nucleus. On a closed loop, the wave must satisfy a geometric requirement to survive. For the wave to persist, its head must perfectly meet its tail. Crest must align with crest. This requirement means only whole numbers of wavelengths can fit around the orbit. Any other path results in a broken pattern that cancels itself out. When we apply de Broglie's wavelength formula to this circular geometry, the terms rearrange themselves into Bohr's exact rule for allowed orbits. De Broglie turned a rigid law into a natural resonance. But this physical picture forces a radical question. If the electron is behaving entirely as a wave in three-dimensional space, why are we still picturing it attached to a flat, one-dimensional classical track? De Broglie proved the electron had a wavelength. Erwin Schrödinger will discard the planetary orbit entirely and write the defining equation for the wave itself.
De Broglie gave matter a wave, but the orbit remained invisible. Next, Heisenberg rejects the orbit and builds physics without it.